Hello and welcome to this tutorial on predicting protein structures using homology modeling. Today I will guide you through the process of predicting the 3D structure of your protein using Swiss model. I will also show you how to evaluate the quality of the predicted models using different quality check parameters including Ramachandran plot. Protein structure prediction is a crucial aspect of bioinformatics and computational biology. Understanding the 3D structure of a protein provides valuable insights into its function, interactions, and role in biological processes. Since experimental methods like X-ray crystallography and NMR spectroscopy are time-consuming and costly, computational approaches such as homology modeling offer efficient alternatives to predict protein structures. Homology modeling is a computational technique used to predict the 3D structure of a protein based on its sequence similarity to one or more known protein structures. When a target protein shares a high sequence identity with a known structure, homology modeling can provide accurate structural predictions. This method relies on the principles that similar sequences fold into similar structures. Swiss model is a popular tool for homology modeling. It automates the process of model building by searching for suitable templates, aligning the target sequence with the templates, and constructing the 3D model. Swiss model is user-friendly and accessible online, making it a go-to choice for many researchers in the field of bioinformatics and structural biology. For this demonstration, we will use the protein Q8NHP1 from Homo sapiens. The name of this protein is Aflatoxin B1 aldehyde reductase member 4. The 3D structure of this protein is not yet solved using any experimental methods like NMR or X-ray crystallography, so predicting its 3D structure can provide valuable insights into its potential roles in biological processes and its interaction with other molecules. The very first step of homology modeling is retrieving the target protein sequence. So we will retrieve the target protein sequence Q8NHP1 from UniProt. Go to UniProt and type the target sequence ID in the search box. Our target sequence protein ID is Q8NHP1. Then click search. Once you retrieve the sequence, now review the basic information about the target protein like name of the protein, gene name, organism, what is its basic function and all. Now we will download this protein sequence in its FASTA format. Now copy the sequence and go to the Swiss model website, which is swissmodel.xpasi.org. I have given the official web address of Swiss model in the description below. Please check it. When you are in the home page of Swiss model, click on Start Modeling. Now paste the target sequence into the Swiss model input box. We will give some project title. Say we'll give homology modeling. Email is optional and I am leaving it blank. Now we have two options. We can either click search for templates or click build models. The main difference is search for templates option will search for sequences which are highly similar to a target sequence with known structures. We can then choose a suitable template of our interest manually and build model. If we go with build model option, Swiss model will do the template search, choose suitable template for modeling and construct the model automatically. For this demonstration, we will go with build model option. So click build model. You can see in the left hand side panel, it shows that your model will appear here when ready and auto model is running. More models are still to be built for this project. So this is actually a time consuming process and you have to wait patiently for several minutes till the models are generated. Once the models are ready, we will review the generated model and analyze the results. We got the models now. Results in Swiss model is organized in 3 tabs: summary, template and models. We are now in models tab. We will first review the summary, then template, and then come back to the models tab. In summary tab, we have the entire project summary. First, we have our target sequence information. Second, we have the template results. Swiss model identified 543 templates which were found to be having higher similarity with the target sequence. By using its own heuristic filtering approach, it narrowed down the number of templates from 543 to best 50 template. So it's showing only the best 50 template here. First column is the template. Second column is the sequence identity. Third column is the bio unit oligostate. And the last column is the description about the template. Say for example, the first best template identified by Swiss model is the protein with the PDB ID 2BPL1. Its sequence identity with our target sequence is 90.65%. Its oligostate is a Homo dimer and the protein is Aflatoxin B1 aldehyde reductase member 2. The second template is 1GVE and its sequence identity is 79.53% with our target sequence, and its oligostate is also a Homo dimer. The protein is Aflatoxin B1 aldehyde reductase member 3. If you click on the show full template details, it will show you all the 50 templates identified by the Swiss model. In this page, we have different tabs like templates, quaternary structures, sequence similarity, alignment, and more. We are in templates tab now. The checkbox corresponding for the first entry, that is a 2BP1, got selected, which means that this protein structure was used by Swiss model for modeling our target protein. If you click on this pull down arrow, you can see more details about the template target alignment and all. The first template is a 2BP1. It is the structure of Aflatoxin B1 aldehyde reductase member 2. This protein structure was solved using X-ray crystallography. Below you can see the alignment between the target and template. Template is covering almost the entire length of target sequence except for the first few amino acids of target. That is, it covers the amino acid from 11 to 331 of the target sequence. Similarly, if we click on the second template entry, which is 1GVE, we can see the details of the template, target template alignment, and so on. The query coverage of the second template is 0.98, which is 98%. The first few amino acids of the target sequence is not covered by this template also. This protein covers the target sequence from 8th amino acid to 331 amino acid. If you want to build the model based on this template, you can click on the build model button. Swiss model will generate the model based on this template. In the top menu, we have the options like coverage, GMQU, QSQU, identity, methods, oligostates, and ligands. We will explore this one by one. Coverage, it is the query coverage. It means that how much the target sequence is covered by the template structure. We need to look for the template which almost covers the entire target sequence. The next is the GMQU. GMQU stands for Global Model Quality Estimation. The GMQU score, which ranges from 0 to 1 and reflects the expected quality of the model. It combines properties from the target template alignment and the template structure. A higher GMQE score indicates a higher quality model. For instance, a score closer to 1 suggests the model is more reliable, where a score closer to 0 indicates lower confidence. For the first model, using 2BP1 as the template, the QMQE score is 0.94, which is closer to 1, and it is a pretty good score. The next value is the QSQE. It stands for Quaternary Structure Quality Estimate. QE evaluates the quality of the predicted quaternary structure of the protein complex. It normally ranges from 0 to 1, where values closer to 1 indicates a higher quality quaternary structure prediction. QE helps determining the reliability of the predicted interaction between multiple protein chains in the model. For the first model, using 2BP1 as template, the QE score is 0.68. We have to note down that this QE score is applicable only for the oligostate of the model, which is not a monomer. So it should be either a dimer, trimer and so on. For monomer, its values will be null. The next is the identity or percentage identity. The sequence identity between the target sequence and the first template is 90.65. The method used for solving the 3D structure of the template protein is X-ray crystallography at the resolution of 2.4 angstrom, and the oligostate is a Homo dimer. And the ligand section we have 2 into NDP and 2 into FLC, which means that there are 2 molecules of NDP and 2 molecules of FLC are co-crystallized with the template structure. The next tab is the models tab. The 3D model generated by Swiss model using 2BP1 as the template is shown in the graphical display window on the right hand side. We can translate, rotate and zoom the molecule using the different mouse buttons. In the left hand side panel, we have the QMEAN DISCO global value as 0.91. The QMEAN DISCO stands for QMEAN Distance Constraint Score, is a specific global quality estimation tool used in the Swiss model server. It evaluates the agreement of a modeled protein structure with experimental distance constraints derived from homologous structures. The QMEAN DISCO score is particularly useful for assessing the overall quality and reliability of the homology models. As I said, the QMEAN DISCO global score, which ranges from 0 to 1, where higher values indicate better agreement with the distance constraints derived from homologous structures. Values closer to 1 suggest that the model is in good agreement with the experimental constraints, indicating a high quality model. The values significantly below 1 suggest that there may be some discrepancy between the model and the experimental constraints, indicating that there may be some potential issues with the model's accuracy. Below to that, we have the local quality estimate plot of the model. Using this, we will estimate the local quality of the model. The local quality estimation plot, which shows the predicted reliability of different regions in the model. The plot displays the QMEAN DISCO local score representing the local quality of each residues. Regions with higher local score indicates higher confidence, while lower score suggests areas of the model that may needed further refinement. In this graph, x-axis corresponds to the residue number in the protein sequence, y-axis represents the quality of the model for each residue measured by its similarity to the target structure. A higher value indicates higher similarity and better quality. Value ranges from 0.3 to 1.0, where 1.0 indicates a perfect similarity. For our model, the graph shows several regions where the predicted local similarity is close to 1, indicating high quality modeling for those residues. These regions are likely to be accurately modeled and have close resemblance to the template structure. There are a few dips where the predicted local similarity drops below 0.8. These areas might have structural discrepancy, or they may have more flexible region in the protein leading to lower modeling accuracy. But the majority of residues have predicted similarities above 0.8, suggesting the model has a overall high quality. However, attention should be given to the regions with lower scores, as they might require further refinement or validation. Below to the graph, we have QMEAN Z scores. The image shows a QMEAN score summary from Swiss model, which includes several components that evaluate different aspects of the protein model's quality. We will now analyze these results in detail. The first score is mean score components, which is given as a QMEAN minus 0.56 for our model. So this is the overall QMEAN score of our model. The value of minus 0.56 indicates that the model is somewhat lower in quality compared to high resolution experimental structures. A score close to 0 would be ideal, suggesting a model of similar quality to experimentally determined structures. Negative values indicate deviations with the magnitude reflecting the extent of the deviation. So the next parameter is C beta interaction, whose value is 0.13. This component actually evaluates the geometry of C beta atoms in the protein. A positive value close to 0 indicates that the C beta interactions are within a normal range compared to high quality experimental structures. This suggests that the backbone conformation of our model is fairly typical. The next parameter is all atom interaction, whose value is 0.96 for our model. This term assesses the overall packing quality of all atoms in the protein. A value of 0.96 is very high, indicating that the atomic packing is well within the expected range for high quality structures. This suggests that the atomic interactions in our model are accurate and more reliable. The next parameter is the solvation, whose value is minus 0.06. This component evaluates the solvation energy, which measures how well the protein model mimics the solvation effects seen in experimental structures. A value close to 0 is desirable. Here minus 0.06 is slightly negative but very close to 0, indicating that the solvation energy is reasonably accurate. The next parameter is a torsion, whose value for our model is minus 0.58. This term measures the quality of the torsion angles, which is phi and psi angle, in the protein's backbone. The value of minus 0.58 suggests some deviation in the torsional angles compared to what is typically observed in high resolution experimental structures. This might indicate regions where the backbone conformation is less accurate. The plot on the right compares our model with PDB structures. It actually compares our model's normalized QMEAN score with a set of non-redundant PDB structures of similar size in PDB. The red dot represents our model. If our model's dot is within the main cluster of points, it indicates that the model's quality is within the typical range of proteins of similar size in PDB. If it is outside the cluster, it suggests that the model may have quality issues. In our case, the red dot is within the main cluster, and so the model quality is pretty good. Quality check is a critical step in protein structure prediction to ensure the reliability and accuracy of the predicted model. Even with advanced computational tools, predicted structures may have errors or regions of low confidence. Evaluating the quality of these models helps identify these issues and provides a measure of confidence in the predicted structure. It also helps in refining and improving the models for better accuracy. If you click on the structure assessment, it will generate the Ramachandran plot using mole probability server. Now we got the results and we will analyze the results in detail. Mole probability results, it gives a detailed assessment of the structural quality of our protein model, focusing on various geometric criteria. The overall mole probability score for our model is 1.10. The overall quality score, it integrates several geometric checks. A score of 1.10 is very good, indicating that our model is of high quality and comparable to high resolution crystal structures in protein data bank. The clash score for our model is 0.91. This score actually measures the number of serious steric overlaps, which is greater than 0.4 angstrom per 1000 atoms. A score of 0.91 is very low, indicating there is a minimal steric clashes, which suggest a well-resolved model. Say for example, in our model B269ARG, B304GLU indicates a specific clash between these residues. Now we will interpret the Ramachandran plot. The quadrants of the Ramachandran plot help identify the secondary structure elements. Top left quadrant corresponding for beta sheets and turns, bottom left quadrant corresponding for right-handed alpha helices, top right quadrant corresponding to left-handed alpha helices and turns. We will now identify the percentage of residues in favored and disallowed region. Residues in favored region indicates a higher quality model. So for our model, we got 96.55% of amino acids in favored region. This percentage indicates the fraction of residues in favored region of the Ramachandran plot. A value above 98% is excellent. So 96.55% is still very good, indicating most residues in our model are in energetically favorable conformations. So we got the outlier score as 0.63. This indicates a small percentage of residues is in disallowed region of Ramachandran plot, which is actually acceptable for high quality models. The next value is the rotamer outlier value. We got 1.35% for our model. This indicates the fraction of side chain rotamers that deviate from common energetically favorable conformation. 1.35% is actually acceptable value. The next score is the C beta deviation. We got 2 for our model, so which indicates deviations have potential local distortions in the backbone structure. Having 2 deviation is relatively very minor and acceptable. The next parameter is the bad bonds. We got 0 out of 5180. This indicates that no bond length deviates significantly from ideal value, which is excellent. The next parameter is bad angle. So we got 40 out of 7028. This metric shows that the number of bond angles that deviate from ideal value. Having 40 bad angles out of 7028, total angle is relatively low and acceptable. So the overall summary from the quality checkers: this model is of high quality as indicated by the low mole probability score, low clash score and high percentage of residues in favored region of the Ramachandran plot. Still, we can make specific improvements in the model. See, there are few amino acids present in the Ramachandran outlier. We can consider refining the regions around the residues which are present in the outlier. So for example, proline 80 of A chain and B chain, these are present in the Ramachandran outlier. So we can refine those regions to make the model better. We also have a few rotamer outliers. So we can investigate and potentially adjust the side chains conformation for this listed outliers, particularly the methionine and glutamic acid residues. We have a few bad angles in the model. We can address the bad angles around the histidine, proline and aspartic acid residues, possibly through some local refinements.